welcome to Learn Extra Live. I'm Katleho and I am so super excited to be back. You don't understand how much I've missed you guys. Of course, we are doing physical science, guys. Physical science is one of your best subjects. I know it is. You don't even need to tell me. So today we are really going to give it our all. We are doing magnetism, guys. It's going to be some awesome stuff because we've got some experiments going. We've got Tracy in the house to show you how everything is and to take you through everything in detail. So please, guys, join us in full force today. You already know that our Facebook page is www, as you know, facebook.com/learnextra. This is where you can post everything that you need to post. Guys, I'm talking questions, comments, anything that you need to say. If you missed me, please let me know because I've missed you too. And of course, Twitter @LearnExtra. Join us on these platforms, guys. They are made for you. We need you guys to ask us questions so we make sure that you grade 10s are ready for an awesome, awesome year ahead of you. Okay. Tracy, please tell us what we'll be doing today.
Thanks so much, Katleho. Well, grade 10s, we're going to be tackling the concept of magnetism today. And we're going to be doing some experiments. We're going to be playing around with magnets and seeing what things are magnetic. And then we're also going to be looking at drawing diagrams. So come with me to the board as I look here quickly. And what we've got in this lesson, well, today we're going to be obviously defining magnetism and a magnetic field. And fields are incredibly useful in our thoughts on science. We're going to draw field lines, and this is something that students often find challenging. And then lastly, we're going to discuss quite a number of applications of magnetism. So, Katleho, over to you. I think you must tell us about future stars.
I think I will, actually.
That's something important. We're going to then head across to look at magnetism.
Awesome. Thank you, Tracy. So, guys, if you haven't seen already, I am telling you now, the Future Stars competition is up on Facebook and up on our website. Guys, this is for you guys. If you are between the ages of 16 and 21 and you've got what it takes to be an awesome, awesome leader, get all your friends to vote for you guys so that you can win this competition, guys. It's really awesome. And if you're a mindsetter, this means that you already have what it takes. So every single one of you literally needs to jump onto the page, jump onto mindset.co.za/learn and check out this competition, guys, and enter it with full force. I know that you guys have what it takes. So please, please do that for me. Don't forget to join us on Facebook. Let me know if you're watching. Guys, I like to know how many of you are watching. If you haven't liked the page yet, please click on that like button. And we've reached like 40,000. It feels like 40 million. So make sure that we reach that 40 million. Okay. Tracy, are you ready for us?
I'm ready. Thanks, Katleho.
Awesome.
So, grade 10s, what I've got in front of me here are a number of different things. We've got some little paper clips. We've got some copper turnings. We've got a little piece of wood with some plastic. We've got some glass, a piece of bronze, metal here, and some wax. Okay, well, in a candle. Now I want to ask, what things are magnetic? So let's try the candle. Definitely no attraction or repulsion there. What about the brass? Well, this is something maybe you're thinking about because you might say, but all metals are magnetic. Are all metals magnetic? Well, let's go across and have a look. Can you see, is there any attraction here? No, there's not. But immediately you can see these paper clips getting attracted to those magnets. Okay, I'm going to pull them off. And watch how, even though they're not touching, they are getting attracted and jumping up onto the magnet, overcoming the force of gravity as they are attracted by this magnetic force. What about the copper? The copper turnings? No, there is no magnetic attraction there. What about let's go with the paper clips. Let's take them off because they are strongly attracted. What about this piece of wood? Definitely no magnetic pull there. Let's try that piece. And we've got some glass here. Certainly no magnetic pull. So the question is, why? Why are certain things magnetic? And you can see this paper clip very strongly being attracted to those magnets. I'm going to put that down and head across to the board, and we're going to talk about why. So let's go across here and speak about some of the key concepts of magnetism. So magnetism is an interaction that allows certain kinds of objects, which are called magnetic objects, to exert forces. And those forces can be forces of attraction or repulsion. Okay? On each other without physically touching. So there doesn't have to be contact between them. You saw those paper clips which were on the ground were suddenly jumping up and being attracted to that magnet. That is because they don't physically have to be touching. They are interacting through a magnetic field that surrounds that magnet. So a magnetic field, what is it? It's a region of space where a magnet or an object made of something that is magnetic will experience a non-contact. Now, by non-contact, remember we said they do not have to touch or be touching. Okay? Magnetic fields surrounding, there are regions of space surrounding magnetic objects will be able to exert that non-contact magnetic force. Okay, so it's a whole area, a region of space surrounding it. The question is why? Why are certain objects magnetic? Well, it is because we have little particles that are charged particles that are able to move. And so if you think about it, if you've got a moving charged particle, it will have a magnetic field. But what I want you to think about here is what substances have moving charges. Well, let's zoom in to every object, every amount, any matter, okay? So let's go, all matter is made up of what? All matter is made up of atoms. Those atoms have, and I'm going to have to draw it down here, a positive nucleus surrounded by these electrons that are able to spin around that positively charged nucleus. Okay? So the focus here is that all matter is made up of atoms and therefore is going to have electrons, which are charged particles. They have a negative charge, which are able to move. Okay? And they're moving very, very quickly. So if we consider an electron has a negative charge and it's in constant motion inside the atom orbiting the nucleus. So that means that every little electron is going to have a magnetic field surrounding it. The question is then, why are some things magnetic and other things aren't? Okay, we saw that little piece of plastic attached to the wood did not have a magnetic attraction to those magnets. Well, why would that be? Here I've got a picture of a plastic ball. And there's the ball. And what you'll notice is that there are arrows in all directions. That is because the electrons that are inside any object, because all objects are made of matter, which have atoms, so therefore have electrons, they are moving, but they have their magnetic fields associated with them. But those magnetic fields point in all directions. So overall, is this thing going to be magnetic? No, because there is no net or total magnetic field for the whole ball. It's got individual little magnetic fields, but they basically overall cancel each other out. They are not all aligned in the same direction. Whereas if we go across to something that is ferromagnetic. Now, this word ferromagnetic is an important word. You need to know it. Okay? Those are materials like iron, cobalt, and nickel they can be magnetized. What that means is that they have regions called domains, regions of space called domains, where the electrons' magnetic fields line up. They all align together, okay? And so there is a net overall total magnetic field. So have a look at this picture. What we've got in this picture is an iron needle, so like a needle that you could sew with, right? It's iron, and it's got these domains, and I'm just highlighting one of them there, where all those magnetic fields point in the same direction. And those ones at the bottom all point in the same direction, okay? In each domain, the electrons' magnetic fields are pointing in the same direction, causing an overall net magnetic field. Then you also have what we call permanent magnets, which have all their domains lined up. Sorry. Let's move it down. So now that iron needle has been magnetized and all the domains are lined up in the same direction, not haphazardly, but now there's an even stronger overall magnetic field. Notice that that is a zoomed in picture of the little iron needle. Okay. Now I want us to go back to these types of magnetic materials that we called ferromagnetic. Ferro refers to ferros, which refers to iron. Okay. So if you think about the symbol for iron on the periodic table, it is Fe, ferros. Okay, that's where this part of the word comes from. Okay, ferros. And I've got a periodic table here that I want us to look at. There's iron. Sorry, we just need a pen. There's iron right there, Fe. Okay, the other two that I mentioned to you were cobalt and nickel. Where are they on the periodic table? Let's go and have a look. Next to iron, you happen to have cobalt and nickel. So three of them all in a row share this property of being able to be magnetized. Okay? Very important that you can identify them, and it's quite simple because they're all next to each other on the periodic table. Let's head back to our thoughts here, and we've got the idea that things are magnetized. Notice that every magnet has a pair of opposite poles. There is a north pole and there is a south pole. Now, it's important to notice that magnetic poles always have a pair. You can't have a north pole without having a south pole. They have to be paired up. By comparison, what we're going to be looking at next week is electrostatics. Okay? And electrostatics refers to electric charges, where we can have a positive or a negative charge all by themselves. Okay? So just watch out for that. Magnetism is very different to electrostatics. Magnetism, you have, when you've got a north pole, you have a matching south pole. Okay? Because think about why. It's coming back to those domains that are all lined up in the same direction. Right? So electric charges, positive and negative, can occur in isolation. You can have one by itself. You can have an overall positive charge by itself. Whereas magnetic poles that would always be paired up. Notice there that like poles, identical poles, would cause a repulsion. So if you had a north pole and another north pole, they will force each other apart. Whereas if you have unlike poles, a north pole and a south pole, they will attract, okay? Attract each other. And when we come back from this short break, what we're going to do is we're going to take a look into representing magnetic fields, and that's an incredibly important section because that's probably what you could be asked in this section. So, Kat, over to you.
Are you ready for a break?
Thanks.
Awesome. I think our mindsetters are like, no, not yet, no break, please stop. But we do need to go for a break. During this break, guys, I urge you to download the notes from learnextra.co.za/live just so that you can jump on and follow along with Tracy, guys. They will really, really help you. So I'll leave you to that during the break, and also maybe get some water, just for kicks. See you just now. Welcome back, guys. I hope you enjoyed that break. As usual, we've got much more to offer you. So guys, jump onto the page. I can already see some questions dribbling in here and there. I'd like some more, guys. Come on. I know that you have questions. I know that there's stuff you want to say. So make sure that you actually post it. Calvin has already said, wow, I took him by a storm of surprise and I've been gone for so long. I know I have, guys, and I really have missed you. So please let me know how physical science has been, how mindset has been, how school has been, anything that you want to know. And of course, ask physical science questions, guys. Anything that you need to know, we are here to help you. Aren't we, Tracy?
Of course. Thanks, Klecho. Of course, we're here to help you. And Apiwe, I hope I've answered your question. Yes, iron, cobalt, and nickel are the only ferromagnetic ones. So absolutely. Thank you for posting that. Grade 10s, we're going to tackle magnetic field lines now, and then we're going to go across and look at some magnetic field lines in action, okay, or iron filings in action, which help us to identify magnetic field lines. So we're going to start by looking at representing magnetic fields. Okay. Remember, we said these fields are the regions of space, okay, where a magnetic force is experienced by different materials. Okay. Sorry, I think I've just done something on the board. There we are, we're back. Okay, so how do we do this? Well, magnetic field lines are always drawn from north to south, okay? Always drawn from north to south. So start your line at north and then work your way to the south pole, okay? And notice that these lines have arrows on them, okay? So it's important that you make sure that they're going away from north towards south. That's number one. Number two, this field is in 3 dimensions, but obviously it's very difficult to draw something in 3 dimensions. And as scientists, we want us to draw these as little models to help represent something. We don't want to complicate drawings by trying to draw in 3 dimensions, okay? So we're only going to draw in 2D, in a cross section. Those field lines never cross, okay? So they never cut over one another because they're showing a whole trend, a field, where the forces would be experienced, okay? We also, as I mentioned, use arrows. Drawn on the field lines would indicate the direction of the field, and that would always be north to south. Strong magnetic field means those lines would be close together, packed closely together, okay? Whereas weaker magnetic fields would mean that the lines are drawn far apart. Now what I've got here is a two-dimensional representation, and I thought it would be nice to identify this with a PhET simulation. So you can go and download this PhET simulation, very useful. There we've got the north pole of our magnet and the south pole of the magnet. And here I've got a little compass, and I can move this compass around. Okay, so this is something that you could go and play with at home if you're unsure about magnetic field lines. Okay, so there I've got the north pole of the magnet. Let's just make that slightly bigger so that you can see that. And there that little compass is pointing with its south pole towards the north. So notice those, if I move it around, what's going to happen to it? It's changing direction all the time. Do you see that? And now, as it's being pulled in, the little red end, the north pole of that little compass needle, is pointing towards the south. So what we've got is this whole lovely curve going from north to south. Okay? Inside the magnet, it's little parallel points, quite useful there as well. Let's try on the other side. Bringing it round. And we can see that compass needle moving and then positioning it once again. Notice that these points on either ends of the poles are very, very distinct. Whereas as I go further away, the magnetic field is not as strong. Okay? Now that is useful to us, and I want us to go back and see how we will represent. So that's our periodic table. Here we are. This is how we would represent this in 2 dimensions. Okay? So there at the top I've got the North Pole, and the bottom we've got a South Pole. This can be in any orientation, it doesn't matter. Okay? But you do need to make sure that the field lines are drawn from north round to south. So from north round to south. Notice specifically here that these directions of the arrow are away from north into south. The number of field lines drawn crossing a given 2-dimensional surface area. So the number of lines cutting through a surface is given a specific name, is referred to as the magnetic flux. Now, we don't deal too much with magnetic flux this year, but next year in grade 11 we start to look at electrodynamics, electromagnetism and electromagnetic field, and magnetic flux is significantly important. So just keep that one in the back of your mind, quite useful, magnetic field lines cutting through a surface. That magnetic flux is used as a measure of the strength of the field through that surface. So it's quite a useful term to know. So let's go with these, and we're going to consider drawing these. We're going to go through 2 questions of those in a moment. Let's go back to look at some more demonstrations, and I've got a couple of things here. So will you come with me to the board? Come join me. And I've got a little Tupperware, and what I'm going to be doing specifically is putting the magnets underneath the Tupperware, because I don't want these iron filings that I'm going to spread all over here to go everywhere, okay? And I specifically don't want them to stick to the magnet, because if they stick to the magnet, it's going to be much more difficult for me to get them off. So here I'm just sprinkling these iron filings all around, and I'm hoping that you will be able to see that they point up and down. Okay, so let me tilt it closer towards you. Okay, and I want you to recognize that they're pointing upwards. They're not just flat horizontally, they are pointing upwards as well. And that's an indication that this is a 3-dimensional field. It's not just 1-dimensional, it's a whole 3-dimensional field. Okay, and actually as I lift that off, the magnet's stuck to the bottom because it's being attracted with these iron filings. I'm going to change the magnet, and I'm going to just come close with the compass here. I wonder if you can see that. Okay, notice the compass will also help to determine the direction of the field. I'm going to take this magnet off, okay, and I'm going to hopefully spread those out quite finely. And here I've got a very strong magnet. This might look small, but it's a very strong magnet. And I'm going to put it in the center, and look what happens as we turn that magnet around. What I'm hoping that you're going to see is there we have quite a nice, strong, from the edge of the magnet, a very strong field. And we've got a significant curvature around with those iron filings. Okay. Now, as I move the magnet, I hope that you can see those little iron filings moving. Okay. Because I want you to see this very distinct curvature. Okay. Now I'm going to throw a few more iron filings on, because I want you to really be able to look at the edges, though that is where the magnetic field is the strongest. Okay, and distinctly we can see that curvature around. Okay, perfect. Let's head across back to the board and tackle a few questions of how you would draw these types of things. Okay, so come with me to the board, because these are the types of questions that you're going to be expected to answer. So, question 1. Unlike poles. Draw the magnetic field when unlike poles are brought together. Predict what forces will be experienced by the magnets. Now, I think I should show this to you as well. We had 2 magnets, and let's try and go back and have a quick look at those. So, I'm going to once again spread out my iron filings, and I'm going to bring some magnets together. Okay, I'm just clearing off these paper clips. Okay, and let's see what's going to happen if I bring 2 magnets together. And I'm going to turn this one around. I wonder if my magnets are strong enough. Let's see if I do that set combined with this strong magnet. Okay, there, that's very interesting. So have a look very closely in the middle there. What's happening? We've got the magnetic field surrounding that strong magnet, and then the other magnetic field surrounding the other group of magnets. And what you notice in the middle is quite a distinct gap. Can you see that distinct gap? Okay. And that is because those 2 magnets are repelling one another. Okay. And so there is a strong magnetic field. There we are. As I bring this even closer, we can see a repulsion between those. Whereas, let me turn this magnet around. Okay. And I'm actually struggling to pull these apart. But as you look closely now, between these 2 magnets, there is no gap. Actually, those magnetic field lines are going directly across. Okay, or the iron filings in this case are going directly across between the 2 magnets. So let's head to the board and see if we can draw and represent those. So head with me to the board. And we're going to be asked, we are asked to draw these. So draw the magnetic field when unlike poles. Well, unlike would be opposite. My screen is not playing with me. Opposite. So that's going to mean a north pole and a south pole, opposite poles together. Okay? When unlike poles are brought together, predict what forces will be experienced by the magnet. Well, let's predict first, because I often find that a prediction will help you in terms of your drawing. So what force will be experienced? And our options are, will it be an attraction or will it be a repulsion? Well, we discussed this right at the end of the previous segment. The idea there that a north pole and a south pole would pull together, attract one another. Okay, so this is going to be an attraction. How would it be drawn? I'm going to put a different color on, and let's draw these 2 magnets. So there's my one magnet and my other magnet. We need to show one as being north and one as being south. So I'm going to show a north, and then I'm going to show a south, right? The idea is that we're always going away from north. So away from north towards south, away from north towards south, okay? And then it will continue. So obviously weaker as you go around, so further apart. Let's just take that last one away. Probably quite strong in the middle, and the arrows are specifically what we are looking for, okay? So something like that. Question 2. Like poles. Draw the magnetic field when like poles are brought together. So by like poles, what do we mean? We mean the same. So our options here, these could be 2 north poles or these could be 2 south poles, but they're the same type of poles and they're brought together. So either you've got a north with another north or a south with another south, but these are like poles. Predict what force will be. So the force is going to be attraction or repulsion. You answer, it has to be repulsion, because these two are the same thing and they're going to force each other away. The diagram that we're going to draw is going to be quite different. Here I'm going to have a north, and so this one's also going to be a north. Then we want to show away from north. And so this curvature is going to be away, and I think, and obviously in both directions. And our arrows, once again, are incredibly important to indicate away. Now, I think it would be helpful for us to visualize what these would be in terms of a memo. And I actually see here, that would be when like poles repel each other. Notice that the arrows are pointing away because that is north and that is another north. They are pointing away. So the field lines we say that they diverge. They are spreading away from one another. On the next page, I happen to have these like ones. Unfortunately, they're swapped around, but it's okay, we can go with that. There we have unlike poles attract. So this one is a north to a south. Okay. There I have from north towards south, and you can see the arrows. I'm just drawing them in for extra to indicate to you that they are always from north to south and very tight at the poles there, very close together. Why? Well, because that's where it's going to have the most highest concentration in terms of the magnetic fields. Okay, so the strongest magnetic field indicated by the lines that are very close together. That is us tackling drawing magnetic field lines, and I'm hoping that really has helped make sense to you, because this is the type of question that you could be asked again. Remember, let's go back to the basics. Magnetic field lines never cross. They are drawn in 2 dimensions, not in 3D, although in reality they're in 3 dimensions. We only draw them in 2 dimensions just to simplify. Always draw magnetic field lines with arrows, because arrows indicate direction, and these things have direction, and it's always from north to south. So I hope that's really helped. Katlego, I think we deserve a break.
I think we do deserve a break. And guys, I can see your questions on the page. I will be shooting them over to Tracy to answer a few of them. I can see that you guys are fully focused. Please do not move off those seats, guys, because there is more still to come. Just see just now. Welcome back, Mindsetters. I'm so glad that you guys are here today, because I know that you guys have learned so much. The questions on the page, I have spoken to Tracy about them. Jackson's question, Tracy, do you want me to read it out to you?
Please read it out to me.
Okay, let me read out. This is by Jackson Somo. He asks, what is the difference between magnetic North Pole and a geographical North Pole?
Very interesting question, Jackson, and it's something we're going to tackle in this next segment. The idea that we've got North Pole and people walk to the North Pole, that is actually, and a North Pole and a South Pole, when we speak about geographic or true North and true South, that is where the Earth spins around, okay? And magnetic North is close, but not exactly there. So we'll be talking about that. Thank you for that question, Jackson. We'll be tackling it in this segment.
Awesome. And do you want maybe another one?
One more. Libya had a question.
Libya had a question, yes. When a magnet is allowed to swing freely on a horizontal plane and it moves and then comes to rest in a more or less north-south direction, what do we call that?
Okay, so my pen, I'm just swiveling it around here as if it's a magnet and it's allowed to swing freely. Okay, that is what we call a compass. And that's what we're going to be talking about now. The idea that it's a needle that's a magnet, that's magnetized, and it's allowed to swing freely on a horizontal plane. Okay, so that's going to be horizontal plane. And what it's going to do is that it's going to align to the Earth's magnetic field. And so will be helpful in terms of allowing us to find direction. So come across to the board with me as we find out some of these things. A compass is one of the applications of magnetism, and it's significantly used. It's used to find the direction of a magnetic field. Okay? The needle is magnetized and is able to line up and would point north-south. When we say north-south, well, the one end will be pointing north and the other end will be pointing south. Okay? Once you know where north is, then you can figure out any other direction. Because if, say, for example, I'm facing north as I look at the look this direction, then behind me would be south. That direction, my right-hand side, your left-hand side, would be east, west. Now, obviously, I don't know which way you're sitting watching this broadcast, but think about it. If you know and you are standing north, then behind you would be south, and you can work out whatever other direction. So there's significant use in navigation. And this is because, well, why? The Earth itself has a magnetic field, okay, which is very similar to a bar magnet. It has a north pole and a south pole. Now, as Jackson mentioned, that's not exactly the same as geographical or true north, but we'll look at that in a moment. So I've got a PhET simulation here, and I've just changed it across from we had earlier this bar magnet, the same simulation. It's a PhET simulation. Just go and Google PhET simulation, magnets and compasses. And here I've got the Earth. Okay, so there we've got Africa over there, North America, South America. So I know that this side up this way is north, and I know the bottom of the Earth, south. What I want you to visualize is inside here looks to be a small magnet. Okay, or not a small magnet, a giant magnet, where we happen to actually have south pole of this bar magnet, similar to a bar magnet, at the top. But surely that's the North Pole. Well, we call it the North Pole because the compass needle points as that is north, because it's being attracted to the top, which is south. Okay, so we call it north, but actually it's going to be a south pole. Whereas if I take this compass needle down towards Antarctica, there we have the compass needle with its south pole pointing with its south pole pointing towards the north, which actually is the south. So it can get confusing. Bear with me here. Okay, let's go back to our notes. Notice that the Earth has two geographical poles. Now that's something we just mentioned and Jackson mentioned a moment ago, where the line of the Earth's axis of rotation meets the surface. So as the Earth spins around on its line axis of rotation, and I'm going to sketch that for you. Let's draw a blue Earth, okay? And the axis of rotation spins around. Now, I'm exaggerating that, but picture the Earth spinning, and we have day, and we have night, and we have day, and we have night, okay? The idea is because of its spinning around that axis, going all the way up to north latitudes, you will have geographic north. Geographic north is also called true north. Now, that picture is, I think, a little bit too exaggerated. Let's just do it one more time. And just like that. Maybe I can take that line away. Just like that. So just off straight. Magnetic north and true north do not correspond exactly. They are actually a small amount out, 11.5 degrees. Okay? So the idea is if you have compass needles pointing, they would point to magnetic north, not true north. Okay? So there we have Africa in the center. We've got that. We've got this axis of rotation that the Earth is spinning around, and we have these magnetic field lines. Notice that they're going away from the South Pole, and they're going towards what we call the North Pole, but is actually the south of a magnet, of looking like a giant bar magnet. Why? Well, it's because our compass needles would be attracted, North Pole of a compass needle would be attracted to the South Pole. So it would point to the top, and so although we call that north, it's actually a south. The Earth's magnetic field is very, very useful because it protects us from being bombarded or having huge collisions by high energy charged particles that are emitted by the sun. There's things like solar wind, okay, and all these different radiation that is being emitted by the sun all the time. And because this Earth's magnetic field is surrounding the Earth, what's going to happen is that particles will be spun off because they're moving charged particles. They're going to have a magnetic field, and those magnetic fields interact with one another, and so experience a force. And so that's helping the Earth to be protected. Okay. Now, I want us to go back to this picture and notice we have got this deviation of 11.5 degrees. That's geographic North Pole, whereas a magnetic North Pole. We call them both the North Poles, but actually it's the South Pole of a bar magnet. I'm going to head back to this, this Earth demonstration. I want us to move the compass around, and let's move it this side so you can see. What's happening here is we're having this North Pole, and north on a magnet is usually the red, okay? The red side of the magnet. Yes, usually. As I move it around, we've got the south being attracted there. There's the North Pole, and it's very similar to a bar magnet. So I'm going to take that away, and there we again have that bar magnet with the representation of the magnetic field lines. Let's move it around. Going around there. Now, the last thing I want us to discuss as we work through magnetic fields and magnetic field lines is to consider the idea of some of the applications. Sorry, wrong one. Some of the applications. I said to you that the magnetic field protects us from the Earth's from the sun's radiation and radiation from space. Also, what we get to see are some spectacular images. And these images are called the solar lights, the northern lights or the southern lights, or the aurorae. They are often called the northern or the southern lights. And they are spectacular red and green lights that stretch across a large part of the sky. So they obviously, it has to be dark for you to be able to see them, but they would stretch across. Now, in South Africa, we don't get to see the northern lights because we're too far north. We're not close enough, so we don't get to see the southern lights in the southern hemisphere. We don't get to see them because we're not close enough to the north and south or south poles. And that is, remember, where the magnetic field would be the strongest, okay? Because as you go further and further away from a magnet, the magnetic field gets weaker, and that's, remember, why we draw those magnetic field lines further apart as you go further away. These northern or southern lights are caused when charged particles from solar wind, so charged particles that are moving, have a magnetic field. Their magnetic field and the Earth's magnetic field interact and cause those particles to spiral along the magnetic field lines towards the north and south poles. If they then collide with particles in the Earth's atmosphere, they can be cause what we call the aurora. And these are spectacular images, but very often only seen like in places like Alaska or Finland or very far north or far south. So in South Africa we don't get to see them, but they are spectacular. One day I'd love to go and look at them.
I'll come with you.
Will you come with me, Kat?
For sure I will.
I'm sure. Maybe that's like something on your bucket list.
Yeah,
something out there that you really want to do. Definitely. So, guys, this is magnetism. This is the amazing world of magnetism. Someone asked earlier, Kat, I can't remember who it was, is my necklace magnetic? Yes, it is. Yes, my necklace is magnetic. And yeah, we can. I'm sure you can experience a lot of magnetism out there. So grade 10s, I really hope that has helped you, that has helped solidify all these concepts of magnetism. We're going to be looking at magnetism quite a lot. We do the foundation as you've done now, and then we draw in electricity next year. And magnetism is an amazing connection. So it's so critical, grade 10s, that you have a firm foundation of magnetism so we can build on it in the years to come. Katlego, are there any questions on the page?
Yes, there actually is. Piwa asked, wow, Piwa, you've been really active on the page. I must commend you. He's just asked, what is meant by magnetic declination?
Okay, that is this 11.5 degrees, if I'm not mistaken. This like deviation away from the North Pole. You can also chat to your geography teacher and find out about that, because obviously we're dealing with the Earth, and so your geography teacher would also want to focus on that. Anything else?
Yes, there was something else. Please may you just clarify about how if you break a magnet in half, and the North Poles and the South Poles and where they belong, just as a clarification.
Excellent. Great question. So I'm jumping back to our start here, and I want us to show these little needles. Now I wonder if the last one is on there. There we are. Okay. So here I've got a permanent magnet, all right? This is a needle, an iron needle, where all those domains have been lined up. Now imagine if I could come along and cut that needle in half there. Well, this side, let's say that this side is the north and this side is the south. Well, what's it going to mean when I cut it in half and break that one there? Well, notice that those domains are all pointing to the right, so then that part would be then south. And this part, excuse the squiggle, will be the North Pole. What if I take another pair of scissors or something and cut another cut there? Well, that's still going to be north, and that part is where the needle, the arrows, are pointing to the right, so that part is going to be south, and this part is going to be north. Notice that you can never have a North Pole or a South Pole in isolation. You have to have them as a pair. Okay. And I hope that answers that question. The idea that no matter how small you break that magnet, you're always going to have the domains aligned in the one direction, so the one way that they're pointing will be the north or the south.
Yeah.
By comparison. So the idea is you can't, if you break a magnet into 1,000 million tiny pieces, it will never just be a North Pole or a South Pole. It has to have always a pair. And that's the big difference between electrostatics, where you can have a positive charge or a negative charge in isolation. You can't ever have one of those, have a North Pole or a South Pole individually. Katlego.
Okay, and one more, just out of interest, Calvin asks, why is it that when you burn a magnet, it turns out It turns out to lose its magnetic nature of attracting objects
When you burn.
when you burn a magnet.
Okay. If you're burning something, it's undergoing combustion.
Yeah.
Very hard to burn iron, to be honest. But yeah, if you were to burn something, it would undergo a chemical reaction and change into a new substance. So
Okay.
therefore, it's no longer going to be those
As
magnets.
powerful. Thank you very
Grade
much,
10s, I hope that's
Tracy.
helped.
Thank
Thanks,
you,
Katlego.
Tracy. Thank you so much, grade 10s, for joining us. You know that the notes are on the page. The page is still up for you. Continue asking questions, guys. Just involve each other and have a lot of fun. I've had fun with you today. Thank you, guys. Bye.